Hello everyone, welcome to my channel Indian School of Physics. This is Nitin here, and today I have come up with a very interesting problem. It is the modification of one of irodove problem. So here is the statement of this problem. A roller belt system contains two identical cylinders of mass m and radius r is having a belt of length L and having a uniform linear mass density of k naught. At any given instant, the rollers are moving with velocity v naught. What will be the kinetic energy of roller belt system? Assume there is no slipping anywhere. The length L and the radius R both are comparable with each other in this case. So velocity of center of mass of this roller is given to us, and it is under no slipping. That means definitely some omega is present in this situation. So let's discuss the concept part of it. For a rolling body, the kinetic energy of this will be given by, suppose there is a rolling body here, and if it is having VCM and there is some omega, so VCM is going to be R omega for no slipping at this point. Alright, and I'm assuming there is a body here that its moment of inertia about center of mass is having form of lambda mr square, where lambda is a number. If lambda is 1, it's a ring or hollow cylinder. Lambda is a half, then it is a disk or solid cylinder. If it is 2 by 3, it will become shell, and if lambda is 2 by 5, it will become a solid sphere. Alright, so total kinetic energy in combined motion we can write as half m VCM square plus half ICM omega square. If I substitute the value of ICM here and using the value of V square is equal to R square omega square, I am going to get this kinetic energy as half lambda plus 1 m VCM square. So this is a very useful result, especially in the situation wherever VCM is equal to R omega will hold. In that case, it can save some time for calculation. Directly we can use it. Now here, kinetic energy of a roller and belt system, I can write it as kinetic energy of roller plus kinetic energy of belt, or chain you can say. So let's calculate the kinetic energy of roller first. So kinetic energy of rollers we can write, since it is in pure rolling and this lower part of the belt, this will be having zero velocity. There is no slipping between any part of the system anywhere. So here you can say this point is at rest, so all these points are instantaneously at rest, and the center of mass of roller is having velocity of VCM, which is V naught. So I can write it as kinetic energy of one of the roller multiplied by 2, as there are two such rollers. So I can write it as a half lambda plus 1 m VCM square into 2. So it will simply become lambda plus 1 m VCM square. If I substitute the value of lambda, I am going to get 3 by 2 m V naught square. This is the kinetic energy of both the rollers combined. Now I'm going to calculate kinetic energy of belt. If you see the belt carefully, it has 4 different parts. One is curved part here, then this straight part, this curved part, and this straight part. Now kinetic energy of this straight part, directly I can say it will be 0 because it is at rest. So K1 is 0. But this part of the belt is having some velocity, and similarly this part of the belt is also having some velocity, and both are identical since symmetry is present. I can say the both will have kinetic energy equally in this round part. And then there is this flat part here. I'm calling this kinetic energy as K2, and each particle on this belt in this part is moving with velocity of 2 V naught. For no slipping, I can say velocity of topmost point is VCM plus R omega. So total kinetic energy of belt I can write as K1 plus K2 plus 2K3. K3 here and K3 here. So 2K3. So now this K1 is going to be 0 here. This K1 is going to be 0 here. Now I'll be getting K2 plus 2K3. I'll be getting this as K2 plus 2K3. So K2 is very simple actually to calculate. Let's say this length is L1. If this length is L1, KL1 is the mass of it, K0 L1 is the mass of it, and 2V0 is the speed of it. So half K0 L1 into 2V0 whole square, and this L1 we can find out from the total length of the belt, which is L is equal to 2L1 plus pi r plus pi r. So 2L1 plus 2 pi r is equal to L. So from here I'm going to get this L1 value as L by 2 minus pi r. Alright, so when I substitute this value, I am getting k naught value as k2 value as k naught times L minus 2 pi r v naught square. So kinetic energy of this bend part now I'm going to calculate. So kinetic energy of bend part. Now if you observe each particle on this belt, so I'm taking a general particle here at an angle of theta, and it is present at this general d theta here. So just see this part. This particle is having v naught velocity due to translation in horizontal direction, and due to rotation it will have r omega in this direction. Luckily r omega is also VCM, so I have to write this vector sum. So here you can write this velocity of this particle as a function of theta is v naught, and this we can find out vy and vx component here. When you simplify that, you are going to get 2 v naught sine theta by 2. So now it's kinetic energy of this part. I can write half dm into v particle square. Dm is going to be k naught into length of this, which is rd theta. So k naught rd theta is the mass of it. V particle is 4 v naught square sine square theta. When I substitute and I integrate from 0 to pi, I'll be integrating this part from 0 to pi. Then I'm going to get this answer as pi k naught r v naught square. Alright, I'm going to get this as the energy of this bend part of the left half. Now I can write the total kinetic energy of the belt as k1 plus k2 plus 2k3. k1 is the lower part, k2 is this part, and k3 is the bend part here. So k2 plus 2k3, when I substitute these values and check, I get a very interesting result that kinetic energy of belt, this RR gets cancelled. It does not depend on the radius of the roller at all. Total kinetic energy of the belt will come as mass of the belt, which is k naught L into v naught square. So very simple result I am getting here, k naught L v naught square. So that is the kinetic energy of belt. Next time onwards I can directly use this fact that kinetic energy of belt is mb into v naught square. So total kinetic energy of this system, I can write it as 3 by 2 mr v naught square, that is the kinetic energy of rollers, plus kinetic energy of belt, which is mb v naught square. When I simplify, I get this expression. This is going to be the answer for this particular problem. So I hope you have enjoyed this solution, and I think this thing was completely new for you, that kinetic energy does not depend on the radius of the roller. So if you have enjoyed this solution and understood this concept, please leave a like, share this video with others, and I'll be coming up very soon with another amazing video. Please if you haven't subscribed my channel yet, subscribe it. Thanks for watching this video.